All waves do four things, whether they're sound, light, or mechanical waves like water. They can reflect, which as we know can cause different outcomes, whether it's fixed end or free end reflection. They can also refract, diffract, and interfere with one another. We've discussed reflection and interference of a wave on a string or in a single plane. Let's examine all three of these concepts, refraction, diffraction, and interference, in a little more detail. Refraction occurs when we change medium. This is why light bends when it goes through a glass of water. You may see a pencil in a glass of water that seems to bend at a different angle. Refraction is why waves crash. They're changing medium by changing depths of water. This is the change in direction of a wave passing from one medium to another caused by its change in speed. We can observe the change in direction primarily when we have an angled wave come in. If we have a straight plane wave come in, we can observe the change in speed. If we send our wave from one medium to another, in this case let's pretend it's a water wave going from one depth to another depth, we observe that as it changes mediums, it slows down. Speed of a wave only changes when the medium changes. That's if we're looking at the same wave. The frequency stayed exactly the same. So if the frequency stays the same, but the velocity changes, or in this case goes down, the wavelength needs to go down. That's why those waves, or those crests and troughs, are closer together after it's changed mediums. Remember, with water, we can assume that different depths mean different mediums. Let's look at refraction at an angle. Change in medium can act like a fixed end reflection. Not only do we see this change in speed, direction, and therefore wavelength because of speed, we also see reflection. When the wave comes in, it reflects and refracts. When we see reflection in this case, the angle of incidence angle equals the angle of reflection. It's the same concept we've seen with reflections on an angle. It reflects at the same speed. Speed only changes when the medium changes. Because it reflects back into the original medium, it does not change speed because it does not go into the new medium. When we see the refraction, it's going to change directions. Imagine a toy cart driving at an angle towards a carpet from a wooden floor. When its first wheel catches the carpet, it's going to have a different level of friction than the wooden floor would, which means it's going to move at a different speed. That one wheel causes the car to move slightly different, which causes it to change its angle. We have the left side, for example, moving at one speed because it's on carpet, and the right front wheel moving at a different speed because it's on wood. This causes the refraction, the change in direction. The speed also changes. Speed only changes when we move from one medium to the next. And then it refracts into that new medium, which again accounts for the change in speed and the change in the wavelength. If the speed goes down, the wavelength goes down. If the speed goes up due to the change in medium, then the wavelength goes up. Let's send a wave at an angle from one medium to the next. The second medium here is represented by the blue box. It comes in at an angle and two things happen. We have one angle or one wave that comes off at the same angle it came in. If you notice, the refracted wave, the wave that continues through the new medium, is moving slower because it changed directions when it changed the medium, but it also isn't going through at the angle it started. It actually is a little turned further down. So the angle changes. The speed changes and the wavelength changes. In this case, we see reflection and refraction. The wave that was reflected, if we notice, moves at the same speed as the wave that was in incidence. To observe diffraction, we have to see how waves interact with obstacles. Waves tend to spread around obstacles or corners. So in this case, we have an obstacle. This almost looks like a door to a classroom. We have two walls. When the wave comes through that opening or that slit, it's going to spread into the shadow of the obstacle. So in this case, those red walls. This is why a loud hallway can be heard throughout a classroom if the door is open. You don't have to stand right in front of the door because the wave comes in, so the sound wave in this case comes in, and it bends or spreads around those corners. It fills in the shadow area, the area behind what would be walls. So it comes in and it spreads around those corners. We often see this with rounded waves. We've discussed interference on a single string before. Constructive interference, you add the crests. Destructive interference, you subtract them, depending on whether it's a crest-crest, trough-trough, or a combination of the two. If it's a combination of a crest and a trough, we subtract. We can look at interference in a little more detail by looking at waves coming from two individual sources. So if a wave is caused by this source, the solid lines are crests, the dotted lines are troughs. We could throw a second source in there. It's going to have waves just the same. Now let's look at what happens if we have both waves going at the same time. The two wave patterns overlap as they're generated. Interference occurs when two waves meet on the same medium. Constructive interference occurs when the amplitudes have displacement in the same direction. That's another way of saying a crest overlaps a crest. A trough overlaps a trough. A crest, if we're looking at a wave pattern from the side, would be up. Trough would be down. We've seen this when we've added the heights of crests or the depths of troughs to show constructive interference. In this example, we can observe constructive interference by finding where the waves overlap. The crests are the solid lines, the troughs are the dotted lines. We just need to find where solid overlaps solid and dotted overlaps dotted. I see that in a couple specific places. I observe that they exist in a straight line like that. We can find those points of constructive interference and then follow through and see the pattern that they create. Because this is constructive, whatever happens here, the amplitude increases. If this was a sound wave, we'd be adding the sound, so it'd be a louder sound in the center there. If it was water waves, we would have higher amplitudes for those crests. These would be higher waves and deeper troughs. Destructive interference occurs when amplitudes have displacement in opposite directions. So really that's whenever a crest overlaps a trough. A crest has positive amplitude, it's up. A trough has negative amplitude, it's down, or negative displacement from the equilibrium. So we just need to find where they overlap, where all the crests and troughs overlap together. These are points of destructive interference. Again, we can connect the dots on those and see a pattern unfold. This is destructive interference. So if these were sound waves, this is where we would not be able to hear sound. If these are water waves, this would be still water. We've learned to observe this phenomenon, especially with sound waves. Look at any theater outline. Theaters are designed around sound waves. The seats are the gray area. The white paths are the aisles. Nobody will be in the aisle, so you don't worry so much about the sound. If we look at that pattern, though, the green constructive interference occurs right where the seats are. Those orange lines, the destructive interference, where the sound would drop out, that's where the aisles exist. So we alternate constructive, destructive by alternating seats, aisle, based on the location of the speakers.